Hello, welcome to Designs for the Edge with Microchip Technology. Designs for the Edge is our ongoing live stream series in which we talk about market trends and system design challenges. We are live streaming today on several social media platforms. Please feel free to make comments, give us a like, subscribe to the channel, and ask questions. We'll try to take some questions at the end of the episode. I'm your host, Eric Glatfelter. Our topic today is accelerating innovation in onboard design systems. Joining us today is Vijay Bapu. Vijay, welcome to Designs for the Edge.
Thank you, Eric. Great to be here.
Glad to have you. For our viewers today, would you tell them what your role at Microchip Technology is?
Sure. I'm a product marketing manager in Microchip's 16-bit division. I work on the DSP controller and power applications.
Okay. So today we're talking about onboard charging designs and systems. This is a crucial element within the electric vehicle. Obviously, there's a multiple set of applications within the electric vehicle. Would you give us kind of a main overview or a high-level overview of the major applications?
Yeah, sure. Yeah, I'll give you a broad overview before we get into the onboard chargers. If you look at the image here, there are various different applications in an electric vehicle. Each of these applications are critical. So if you're starting from the bottom left, we have a DC to DC converter. Any EV requires DC to DC conversion. And if you're just going clockwise in this diagram here, the next item is a regenerative braking system. It involves an inverter. Then, of course, we have an electric motor in any electric vehicle. Mm-hmm. And for in-cabin touch and sensing, we have hands-off steering wheel detection. And that's an important feature as well. And another next item is the acoustic vehicle alert system, or what we call as e-sound. So when the EV is backing up, you hear that sound that is generated. So then, of course, in any electric vehicle, you need thermal management that is required. And of course, to power the EV, you need off-board chargers, and we have solutions for EV charging as well. Okay. And a critical part of an EV is the battery management system. Yeah. And of course, lastly, on the lower right is the onboard charger that we will talk about.
Right. Okay. Now, all of these electric systems, electric applications require electricity, which is coming from the battery. That battery gets depleted and needs to be replenished, which brings us to the onboard charging system. So that's a complicated system within itself. So how do we generally partition that onboard charging system?
Sure, yeah. So typically an onboard charger consists of a PFC stage and a DC to DC stage.
Okay.
The PFC is like the primary side and the DC to DC is the secondary side.
Okay. So let's take them one at a time. So tell us a little bit more about the PFC system.
Yeah. A PFC is required in almost any AC to DC conversion. So the objective of the PFC is to make the input to the supply look like a simple resistor. So this helps with optimizing efficiency and minimizes losses. Okay. So in our case, we are using a boost PFC for this application. So if you look at the image there, essentially we have what is the unit there, that is kind of the reference demonstrator. So we have a power board there, and the power board is the base board, and to which we have plug-in modules available for the DSP as well as the Silicon Carbide. So essentially we can do a lot of prototyping with different DSPs and different Silicon Carbide FETs before you actually lay out your final board and make your final design. So it helps with a lot of prototyping and development.
Okay.
So for the DSP, in this particular design, we use a dual-core DSP. So essentially, the secondary core of the DSP runs the PFC algorithm. Mm-hmm. We have a tight control loop for the PFC on the secondary side. And the main core essentially manages some of the housekeeping functionality and communication with the rest of the system.
Right. Okay.
For this particular totem pole PFC, essentially we have 2 high-frequency half bridges and 1 low-frequency half bridge. So in single-phase mode, we are essentially transferring about 3.8 kilowatts of power. And we have the low-frequency bridge closing the loop to neutral.
Okay.
And in interleaved operation, this design can support up to 7.6 kilowatts of power. Also, we provide good software with this. There is essentially a nice software architecture that has been set up for this. There is a scheduler, simple scheduler for coordination of tasks, and we provide compensation coefficient code that is generated by tools like the DC-DT and PowerSmart as well.
Okay.
An important part of the system is, of course, the silicon carbide FETs. That is very crucial for these kind of voltage applications and for the switching frequency. And this helps maximize the system efficiency for the overall PFC, because that is where a lot of the current is flowing through in the system.
Right.
So you get more than 98% efficiency over a broad operating range for this PFC.
And at these power levels, every percentage of increased efficiency contributes a lot.
Exactly, exactly, yes.
Okay, okay. So we talked about the DSC and the silicon carbide FETs here. Are there other components that Microchip is contributing to this design?
Yes. The gate driver as well
Sure.
is a crucial part of the design that helps put the silicon carbide FETs in the right state. And of course, there are also buck and boost regulators for biasing that are required for the overall system.
Okay. Now, in this graphic, we're showing a board in the upper right. That's something that customers can get a hold of?
Yeah, absolutely. Please reach out to your Microchip sales representative, and we can enable access to the board. And also, we can provide you all the documentation for things like schematics, design files, and all of that good stuff.
Yep.
Once you sign the right terms and conditions.
Okay, great. Okay, so that's the first stage, the PFC, and then from there, the second part of the partition is the DC to DC converter.
Yes, this is another, of course, crucial part of the OBC. The DC to DC converter here is a dual active bridge topology. So the DC that comes out of the output of the PFC is converted to the right voltage to feed the battery of the EV. So we use a dual active bridge controller for a couple of reasons. If we look at the dual active bridge here on the image, we have a primary side essentially inverter. It's a full bridge inverter, and on the secondary side is a rectifier. And if you look at it, there are two key components. There is a shim inductor and a transformer for the energy storage. So essentially, the primary side converts the DC to AC, and a lot of the efficiency is determined by how the shim inductor and the transformer are defined. In this dual active bridge, what we are doing is we are using phase shift to control the power transfer.
Okay.
So essentially what we're doing is we modify the phase shift of the switches on the primary side and the phase shifts on the secondary side as well. And also the delta between the two phase shifts are used to control the power transfer.
Okay.
The shim inductor that is mentioned as an SR choke here is a crucial component of the design. That is what really manages the power conversion in terms of the storage in this particular design. And we use Litz wire for this. The reason why we use Litz wire for this is because there are high frequency components in this in the current in this design, and as a result, there can be losses due to skin effect, and the Litz wire helps minimize those losses.
Okay.
And similarly here as well, we use a modular approach here. We have a power board, we have the DSP pins,
Yep.
and we have the silicon carbide FETs as well on pins to optimize your solution before you make your final design.
Okay. Okay, and so sort of same two questions as on the PFC. First of all, we talked about the DSC and the silicon carbide, which in this case is in the modules. Other components here as well, other power management components from Microchip?
Yeah, similarly, the gate drivers and also some of the biasing regulators, some DC to DC converters, LDOs, and some of those as well.
Okay, and we're showing a board there. What is the status of that board?
We have all schematics and design files available now please reach out to Microchip sales representative, and the board will be available for sale probably in about a couple of months from now.
Okay. So in development. Great. Okay, so we've got the two main stages there of the onboard charging system. So that gets the current into a usable format and charges that battery. From there, to distribute that energy from the battery to all those applications that we looked at earlier, we now need to convert the other way. So tell us about that converter system.
Sure, yeah. So this is what we call as the low voltage DC to DC, essentially converting the DC voltage from the 400 or 800 volt EV battery down to an auxiliary 12 volt battery in the system. Okay. So the reason why we put these two together is we see a common trend in terms of the kind of controllers used for the power conversion for these two, and also we see similar design teams working on these two applications.
Okay.
And we also see a convergence of these two into one physical unit. We hear the concept of one box,
yep,
which is an interesting trend that we are closely following. So that's why this goes well with the onboard charger.
Yeah.
So in this case, what we do is we use a phase shifted full bridge topology. So there's two half bridge on the primary side, and the secondary side is slightly different from the dual active bridge in that there are two buck regulators. If you can see the image there are two buck regulators in parallel. You can see the two inductors there, and this is what is really powering the output cap. So the two buck regulators in parallel essentially help minimize the maximum current through each of those inductors, and you can scale those inductors appropriately. And the parallelism also provides some redundancy in the system.
Okay. So there again, a lot of different Microchip offerings contribute to that system solution.
Yeah, exactly. There's a DSP controller, there are some gate drivers, and also some biasing regulators as well.
Right. Okay, so we've talked a lot about the power management stages. Let's step back and talk about the whole vehicle a little bit, but there's also kind of an ecosystem that goes around anything in the automobile, and some of the critical components that are getting a lot of attention right now are security, and the other thing would just be, safety, ASIL safety and things like that. Can you talk a little bit about how those apply to these systems that we've just talked about?
Absolutely, Eric. Yeah, so that's a very crucial point. Just the power conversion functionality is only one piece of the puzzle in an automotive environment. Each of these controllers and these systems have to be integrated well into the automotive environment. And for that, we have a full set of ecosystem and tools that go with our DSP.
Yeah.
So for example, now there is a need for integrating all our software into the AutoSAR environment, so that there is a common platform for ease of development. So we provide the appropriate MCALs for easy integration into the AutoSAR environment. And then, like you mentioned, safety. Safety is very critical, especially for applications like onboard chargers. So we have safety manuals, diagnostic libraries, FMEDAs that go along with our controller, and we can guide our customers through an entire safety development flow.
Okay.
And like you mentioned, security as well. Node authentication is very crucial, and we provide secure elements that go along with the DSP and match it well, so that provides reliable node authentication for each of these controllers. And of course, the entire ecosystem in terms of the software and the tools that really help you get started with your design and help you take it through.
Okay, so these things should make it a little easier to move forward quickly with your design,
exactly,
or a little faster.
And make it and hopefully make it seamless.
Yeah,
make it easy. Yeah.
Excellent. Okay, great. So thank you very much for that overview. At this point, let's check our social media feeds and see if we have questions from the audience. And let me just find my right channel. There we go. So we do have a couple questions. So the first one is about the first subsystem that we talked about, PFC. Why choose the totem pole architecture for the PFC system?
Oh, that's an interesting question. Yeah, sure, I can talk about it. So the totem pole PFC is essentially developed using synchronous FETs.
Okay.
for the boost stage. As a result of which, this helps with bidirectionality. So in the onboard charger, you're transmitting power from the AC source to the battery, but we can also have the power flowing in the other direction if we have a totem pole PFC. And this totem pole PFC helps with optimizing efficiency. So when I talk about bidirectionality, if you're transferring, why would you want to transfer power from the battery to the other way? So for example, in an application where you're transferring power from the vehicle to the grid or vehicle to a load. So in a campsite, if you want to power a tent, you can use the battery in the EV to power that. So you can essentially transfer power the other way.
Right. So if you're doing some glamping and you want to have some lights and music,
exactly.
you can use the car as power. Okay. So the second question is very similar, but about the second subsystem. Why choose the DAB topology over CLLC for the DC to DC converter?
Oh, nice. That's an interesting question as well. Attentive audience. Okay. So the reason why we chose DAB is that the DAB provides a high efficiency over a broad operating point. In this case, the load is varying. So based on the amount of current that needs to be put into the battery, the load is varying. And also the voltage on the battery also varies as the battery is being charged. So in that kind of an application where the load is varying, the DAB provides a better efficiency over a broad operating range. The CLLC works well for a specific operating point, but it's much easier to control a DAB topology over a broad operating point.
Okay. All right. Thank you for that. Okay, next question. How can we get access to the boards? So I think we touched on that, but let's just restate. If people want access to the design files, where can they go?
Yeah, please reach out to your Microchip sales representative, and it will come through the appropriate channels to us, and then we will qualify the leads and we'll provide all the appropriate information.
Okay, great. And looks like that is the last question. So we'll wrap it up there. Again, Vijay, thank you so much for joining us and sharing your expertise on that. To our viewers, thank you for taking some time out of your day and joining us. Please visit us at microchip.com/automotive, and there you can see all kinds of information, the ecosystem that Vijay was talking about. And also visit us at microchip.com/designs for the edge. Therefore, there you can see additional information about our next couple of episodes, and you can also peruse our previously recorded episodes. Thank you again for joining us. See you next time.